Hello everyone. Because of the problem that happened today during the actual live session, I am taking the opportunity to record the session again. So I'll just share my screen with my notebook and I'll go through what we have done today. So let's get back to what we were doing until the last session. Until the last session, what we have done is we have imported the required libraries. We have added a constant in X. X is the set of feature data, which in this case is TV. Y is the series of sales, which is my target value. Now, when we used in the last session the stats models API, we added a constant, and by adding a constant, we were able to model the data in a way that stats model package needs to run the single or simple linear regression modeling, post which we did a fit of the model. We were able to predict the value, and we could also get the SLR summary, right? So once we have got the summary, this is how it looks like. And here we have got a lot of values. Let's quickly revise what we could understand from here. The most important thing being the R² value. This value being very close to 1 or reaching the value of 1 is a very, very good indicator that our model is very good. And so is this value, which is basically my p-value. And because this is statistical inference test, this p-value should be less than 0.05 so that we can reject our null hypothesis. And hence, we can clearly reject the null hypothesis that there is no relationship between TV and sales, or the investments that we do in TV as opposed to the sales or items, a number of items that we sell. Here, because it is e to the power minus 74, it is very, very small, as we can see over here as well, or the constant. This constant represents theta 0, and this line represents theta 1. So this is the value of theta 1, and this is the value of theta 0. And we can get an equation which we have already seen earlier, which looks like sales is equal to 6.97 plus 0.056 of the investment which we made in TV, right? This is the model which we got in the last session which we did. Now let's move ahead and let's look into the residual analysis which we looked into. So the first thing that we looked into is this. There is a normal distribution of all my residuals, which gives a very good confidence, for which we have used this piece of code, which gives us a very, very good confidence that obviously we do have a very nice model, and there is not much problem with the error terms which we see over here, right? We cannot call this as a very perfect linear model, or we cannot call this a very perfect graph, but it is very close to being centrally skewed. So that's what we are primarily looking for. Similarly, if I come down, we had to start looking into the homoscedasticity or homoscedasticity thing. So let's just look into that, and let's go back to our main folder, and we are going to look at quickly the definition of what is homoscedasticity. For that, we are opening our notes, and in our notes, we have already written down the 4 common assumptions of simple linear regression, which is to a very good extent applicable on multiple linear regression as well. And the assumptions are something like this. If I come down, there is a linear relationship between x and y. This we have already seen. The error terms of the residuals are normally distributed. We have already seen this. So now we are going to look at point C and point D. Unfortunately, there is no direct way to look at point C, because this is the distribution of error terms for each and every predicted value yi hat. Yi hat being a terminology which we have discussed earlier as well. And this is, or there is no easy way to calculate this. But homoscedasticity is a terminology which is used for cases or for a situation where all error terms have a same or similar variance. So these two can be proven at once, or these two can be looked at once, for which we have written this small piece of code where we are taking feature being equal to advertising in brackets TV. So we are taking the TV variable, and then we are doing a scatter plot of this feature and my residuals. Residuals is something which we have calculated earlier. Let's quickly look at what is residual. RES is basically the residual, which is the actual value minus the predicted value of the target variable, which is sales. Now, if we look at carefully this diagram, then what we can infer from this is, let's take a line and let's try to draw the line from this 0 point from one side to the other side. Okay, if I'm able to draw a perfect parallel line to the x-axis, x-axis in this case is the range of features, and y-axis is my residuals or the error terms, I can clearly see that the range of the residuals falls somewhere. I can't say exactly, but somewhere from the central line, which is from 0 to plus 3.8 until minus 3.8, right? So other than this, there are other values as well. You can clearly see there are some values over here. There are some values here. There are some values here. Obviously, there are values, but this portion is really the place where everything is condensed, and we can say that each and every of these dot being representative of the residual for each and every estimation that our model has done. It all lies between this range of 0 to plus 3.8 and 0 to minus 3.8, right? So hence we can quite confidently say that although we did expect this gap to be a bit more short, had it been the case it was a bit more short, we would have loved it even more, in which case our R square value may have been even better. But in this case also, with an R square value of 0.8, this is not really that bad, right? I mean, the variance is not really going out of bounds. Now, what do I mean by variance going out of bounds? Let's clear this diagram. Let's try to draw another diagram. So imagine that if we would have got a graph which looked something like this, where the central line would have been something like this, and the variance line, okay, or the upper bound and the lower bound would have looked something like this, right? Then in that case, it would have been very difficult for us to have confidence on the model, because on the lower values of x, there is one variance of error terms. As the value of x-axis increases, the residuals increase. As the value of x increases, the variance of residuals increase more. Why is this a problem? Is because let's quickly write down the formula of our simple linear regression, which is theta 0 plus theta 1 multiplied by x plus a very commonly known error, right? Now, if I have, let's say, let me take the pen, theta 0 we can calculate, which we have already done. Theta 1 we have already calculated. X is my given value. Y is my unknown that I'm trying to estimate. This error will always be there because of estimation problems and because of a lot of data generated scenarios or data related scenarios, so on. This can never be, I mean, we can try to, make this equal to 0, but it can never be equal to 0. So that is the reason why our target although is to make it 0, but it can never be 0. But imagine a situation where this error term is actually something like this, or the variation of the error term is looking something like this. Then this entire equation ultimately will become very unstable. So rather than that, if I have an equation which is something like this, then in this case, the variation is under control, and we can clearly say that my error terms are also under control. All right. Now, we are going to look at another modeling method where we are going to make use of the Scikit-learn library. This is the documentation of the Scikit-learn library. I'll just open the link. I'll also share this into our LMS portal, but you can search this on Google as well. Scikit-learn.org. Always look for the stable version. But before looking into the highlights of the documentation, I would strongly recommend that this is a very generic purpose, production ready API-based programming interface or API-based library, which is available in Python, which helps us to do machine learning, which can be directly put into production as models, right? When we look into models that we are going to put into cloud services, when we do hands-on in there our concepts will be more clear as to what is really a production service or what is really a solution that runs on a production service basis machine learning implementation, but Scikit-learn is obviously one of the very good libraries that we can make use of. However, the reason why I was highlighting the version is that this version should always be looked before we look into the user guide. Right? Before we look into the user guide or the documentation for this library Scikit-learn, we should always verify whether this is the same version that we are using in our local system or not. Right? If you Google, you'll be able to find the exact command using pip command line tool, by means of which you can check the version of the library, and then you can be very, very confident, right, that whether or not you are looking at the right documentation. Obviously, these are open source libraries, so you can also look at the code for Scikit-learn being onto GitHub. It is entirely an implementation done using very low-level languages like C, C++. There are APIs available by means of Python that we are using over here, right? So all the code is available over here along with the documentation, right? Now, let's go back to the modeling page. In this page, what we are doing is we are now going to use escalant to do the predictions once more, or do the estimations once more, and see how this library, although being a black box a solution, as I've already mentioned over here, it is a black box. It is not like stats model where you get a lot of, or a big table or a tabular output where you can find out all the values at once and exactly see what kind of statistical tests are being performed. This is a black box solution, which is also, we can say, production ready, because it provides us with easy set of APIs, right? Easy set of APIs that we can simply call, and we can get the model as well as the parameters of the model and the metrics of the model, right? We'll come down to metrics in a moment. We will cover one very important metric as of this session, and then we'll continue in the next, right? But as of now, what we are going to do, we have again created a variable X for the feature variable, which is TV, and we have created a variable Y with the target variable, which is sales. And then again, we have created X train, Y train, X test, X train, X test, Y train, Y test using train test split, right? So this is something we started doing newly. This is also from the Scikit-learn library, where the inputs are my feature variables and the target variable, and I define a training size. The reason why I do this is because if I would like to simply draw or simply represent a one-dimensional representation of any feature X, then that will be simply points on a straight line, right? So you can just imagine that there are points on this straight line. Maybe these points are going to look something like this. There is a point over here, right? There is a point here, there is a point here, there is a point here, and so on. So in our data set, we have 200 points, right? So our sample size for features is 200, right? So we have 200 points. And what we intend to do is that we are going to randomize using this method that we are seeing over here using train test split. We are going to randomize the selection of X and Y into training set and testing set. The training set will be used, okay? The training set will be used to build the model, okay? Build the model, and the testing set, okay, is going to be used to test the model, right? Okay. The advantage of doing this is that if we build and test our model on the same data set, there is no guarantee that when we put the solution into production, it is going to work. It is the same kind of an analogy which we can take, is that we are studying a book, okay, to give an examination. Let's say we are studying a physics book to give an examination for physics for 10th standard or 12th standard. Although as per NEP as of date, there is no longer a 10th standard, but if we can imagine the days when we had appeared for class 10 and class 12 examinations, if we look at our physics books, if let's say we are studying a physics book and we are going to appear for a physics exam, imagine the test questions, okay, or the questions that you have seen in the textbook are exactly the same questions that you see on the exam paper. Then ultimately all you need to do is to mark up all the questions and the answers in the book, and you can go for the exam and you'll get 100 out of 100, right? But that's not a very good test whether you are a good student in physics or not. That is the reason why it is usually the same format or the same nature of questions you see in the examination, but the questions by themselves are actually different. So that is the main reason behind creating a test set which is used to study, and then a train set which is used to study. I'm sorry, a train set which is used to study a training data to train yourself in any subject. In this case, my linear regression model, and then a test set where you are going to test how good or how bad you are, right? So that is the reason why we are doing this with a value of training size equal to 0.7. This means I'm going to take 70% of my data as training and 30% of my data as testing with a random state equal to 101. Now, this is a very important thing. What is random state? Okay, there are many algorithms by means of which random state is defined, but random state is basically a random seed. I take a random seed, and from this seed, I take the value, I put it in my, let's say, training set. Okay, and then again, I take another random value, I take another random value. But if I keep this random state is equal to 101, then the seed which is used to take the values, which is something like this, I take this value first. My random state in this case is 101. I go to this end, I again come back and calculate 101, and I take the next sample. I again go back, take 101, take the next sample. In this case, what happens is, if I keep a random state, and then overall my my Jupyter notebook here, where I'm creating this model, will be reproducible in the sense, if I share this Jupyter notebook with anybody, then the results that I'm getting in this model, in this example, in this video, is going to be exactly the same as what you're going to get in your side as well. Right, so that is the advantage of using random state. You can read about it over here. Let me just clear the drawings and go back over here. You can read about it here, where there is a very good explanation of what is random state. Okay, a random state is just one number. You can guarantee that the output of run 1 will be equal to run 2. Okay, so this is where they have already given an example to show you what is random state. Okay, it is basically some fixed number, right? Then you can also read about it over here, escalant model selection trend test split. Here you have the variable called random state, which simply, by the definition, a random state is basically, it controls the shuffling applied to the data before the split of test and training data is applied, right? If we pass an integer, then it helps us to get a reproducible output across multiple function calls, right? So that's the thing. Now let's get back to our page, and here there is only one thing extra that we need to do in case of scikit-learn. The same thing or similar thing that we have done in case of stats model is because in scikit-learn there is a small limitation with respect to single linear regression, where out of the box it does not help. Okay, it does not help add the default value, so it does not reshape our, or it does not help to shape the data set into the way uh, in which the model wants, or into the way in which we would like to calculate if there is a single feature. Okay, this would not be the case. Okay, this would not be the case if we were doing multiple linear regression, which we will also see soon. But in case of single linear regression, unfortunately, we have to execute commands like this, where we are taking the value of xtrain and value of xtest. As you can see, this exercise is applicable only on the feature, not on the target, right? Similar to what we have done with stats model earlier as well. We are taking the training values, we are taking the testing values, and we are doing a reshaping of the last element. We are taking a -1, and then we are doing a 1, which simply means that we are adding the constant that we need, right? We are simply adding the constant which we need to create the model, right? And that's exactly what we are doing over here. Okay, once we have done this, right? Once we have done this, then we can say that we are ready. Okay, we are ready with the new kind of model that we can do. For doing what, we can now fit our model, and we have to first of all create an object of the linear regression method. Or linear regression is basically a class. This is the constructor that I'm calling, and I'm creating an object named LR. Okay, now in this LR, I'm going to pass the training data. As I said, I've split my data into train, X-train and Y-train. X-train and Y-train is going to be used for what? To build my model, to study physics, right? This is our example. So we are going to train the model using X-train and Y-train. That's the two parameters I'm going to pass in the fit function, and I'm going to get the linear regression model, right? Once I get the linear regression model, what I'm going to do, let me scroll down. What I'm going to do, once the model is built, I don't have to worry about any table because this is a black box solution. Now, what I need to do is simply call the requisite set of APIs. And by calling the requisite set of APIs, I will be able to get the outputs which I really want to look at. The basic two outputs I need to look at is the intercept and the slope, right? So I need the theta 0, which in this new model is 6.8734, which is quite close to our previous model, although not exactly equal. Okay, that is the way that we can actually differentiate the previous model with the new model. And then I get an array like output for the coefficient is basically my slope. And this one, if you look at the three places after decimals, this is exactly the same of what we have got earlier. But this one, if you look at this and if you take a value which is 6.87, this may not be exactly the same. Let's just quickly check what was there earlier. Let's go ahead and let's check what was there earlier. If you see, it was 6.97 earlier. Okay, and now what we have got over here is 6.8734. So this gives us some kind of a question as to whether we are really going to trust the new model or the old model, because this value is actually different from the older one. Okay, but to test that, we have to look into other values, like although the coefficient of the slope is the same, the intercept is actually different, and that is got by means of model object, which is LR dot intercept. So this is the method, or this is this is the variable that I'm calling. This variable has this value already calculated when we have fit the model. Okay, now let's try to verify whether the new model is better or the old model. So we already know R² value is a very good coefficient or a very good metric, right, to find out how good or how bad the model is. You can look at the Scikitlearn documentation where you can find that there's a library called escalant.metrics, which gives us the R² score, which is otherwise the coefficient of determination, right? Best possible score is 1.0. All right. A constant model that always predicts the expected value of y gets a score of 0. Okay, disregarding the input feature would get a score of 0. So 0 means it is a very bad model. 1 means it is the best model. So obviously I need to import this available functionality, and I need to call this function. So to do that, let's get back to our notebook. And what I have already done is I have added this line over here. As you can see, I have added from escalant.metrics import R2 underscore score, and I've given it a comment that this is imported to get the R² score of the model. All right, so this is what we have already done. We have already executed it. So let's get back and let's come down and let's see what is going to happen now with the modeling phase. So after the modeling, what we are doing is we have to find out the R² score. But if we look at the documentation, it is saying that R² score obviously is going to be a comparison between the true values of y, or the actual values of y, as opposed to the predicted values of y. So that's why the two values that you see over here at the first place, everything else is actually optional. The true values which are really important and mandatory is y true and y pred. In our case, y true is nothing but y test, right? Because we are going to test the model on the testing data. Okay, we have trained it using training data. We are going to test it using training data. So for us, y underscore true is nothing but y underscore test in our case. But what about this y pred? We have not got y pred. We have not predicted as of now. So that's why we are writing this line of code over here to predict the values of y using our model LR and using this method predict, where we are passing the features test values, not the training values. We have used training to train the model. Now you are passing the test data, or X test, that we have already found out using train test split to get all the predictions, right? Now that we have got the predictions, we can calculate the R² scored by passing y test and y pred, and it will give us a value which is approximately, if you take these three or three places after the decimal, you will find it is 0.81. Let's try to see whether that is exactly the same or not as we have received earlier. If I look at this, it is actually exactly the same that we have got earlier as well, right? So model wise, right? Model wise, I can clearly say that my old model and my new model, although the intercept is actually different, right? Which I have already written over here. The new model is slightly different from the previous model because the intercept is not the same as the round, is not the same as the previous one, while the rounded value of the slope or the coefficient of x, right, is the same, right? The slope is the same, but the intercept is not exactly the same. But the R square value is exactly the same until two places of a decimal. So we can see that our new model is almost exactly, we cannot say exactly, but it is almost exactly the same as the previous model with not much difference, right? This metric R squared that we have calculated over here, which gives a value like this, 0.81, also tells us that it is overall a very good model because our target was to make this as close as 1, right? So that's what we are going to cover in this session. As of now, we are going to continue tomorrow with multiple linear regression, and we are going to see using the same data set, or maybe we can take a different one as well, as to how using Scikit-learn we can do multiple linear regression. But before we do multiple linear regression, there is always a question that is still there, or always a question which is which will always be there, is that how, okay, how is going to or how are we going to improve the model, right? There are some techniques, I can say, that we can apply, things that we are going to look into the next session, which helps to better the model. These techniques are known as scaling techniques. Okay, so these are techniques by means of which we can scale our data, and usually there are two very important techniques which are used. One is called min max scaling. Okay, min max scaling, there should be one, and let me just remove this min max scaling, and the other method is known as standard scaling. Right, by scaling the data, what we are doing is we are ensuring that we get a better R square value. Why is this the case? We have already seen this earlier. If we have, or we have already discussed this earlier at least, that if we have a data set where I have one kind of scale, and then for any other scenario, for any other person or any other data scientist, if I change the scale, then the value of R square is going to change, because the value of R squared is actually dependent on the scale at what you are taking the data, right? That is the reason why, that is the exact reason why if I do scaling of my data, if I do scaling of my data, then I will get a model which is really reliable across or irrespective of the scale in which the data was given in form of input. So that is exactly what we are going to do in the next session. Most probably the best way, or a very, very good way, right, to do scaling is the standard scaling, right? So we are going to use the standard scaling, and we are going to see if that standard scaling is going to help, right? Is going to help us doing any betterment to the model or not. We are going to use scikit-learn. We may want to use OLS as well. It doesn't matter. In both the cases, we are going to see if these scaling techniques are going to help improve the model overall. Right? We are also going to discuss a few more things in depth with respect to scaling. Right? Okay, friends, as of now, that's all from my side. Let me just save the notebook so that I can share it across with you. And then uh, we are going to continue tomorrow. Thank you so much.